Alright, let's go. Number 10, HD 140283, Methuselah Star. In 1912, astronomer Annie Jump Cannon cataloged a seemingly unremarkable star in the constellation Libra, just 190 light-years from Earth. For decades, it remained a footnote in astronomical records. Then, in the early 2000s, Howard Bond and his team at the Space Telescope Science Institute used the Hubble Space Telescope to measure its distance with unprecedented precision. What they calculated next should have been impossible. The star's age came back at 14.46 billion years old, give or take 800 million years. The universe itself is 13.8 billion years old. A star cannot be older than the universe, yet the mathematics kept insisting it was. HD 140283 is a subgent, a star in the twilight of its life, with surface temperature nearly identical to our sun. But its chemical composition tells a different story. It contains just 1/250th the iron content of the sun, marking it as a relic from the universe's infancy, formed when heavy elements were vanishingly rare. Every measurement confirmed its ancient nature. Every calculation produced the same impossible result. The paradox forced astronomers into uncomfortable territory. Either their stellar age-dating methods contained fundamental errors, or the universe's age was wrong, or something stranger was happening. Subsequent refinements adjusted the age to 14.27 billion years, with error bars that technically overlap with the universe's age. Within uncertainties, the math now works. Barely. But what makes this particularly unsettling is how close we came to discovering a genuine impossibility. The star exists at the very edge of what physics allows. If measurements had been slightly different, if the universe were slightly younger, or if this star were slightly older, we would face a paradox with no resolution. Somewhere in the cosmos, there might be another ancient sun whose age doesn't overlap, whose existence cannot be explained away by margins of error. Number 9, the Methuselah Planet. On July 10th, 2003, NASA announced a discovery that rewrote the history of planetary formation. Orbiting a binary system in the globular cluster Messier 4, approximately 5,600 light-years from Earth, astronomers had confirmed the existence of a planet. Not just any planet, but one that had been circling its stars for 12.7 billion years. When this world formed, the universe was only 1 billion years old. Earth wouldn't exist for another 8 billion years. The Milky Way was still assembling itself, and somehow, in an environment that should have been hostile to planet formation, this gas giant coalesced and survived. The planet orbits a pulsar and a white dwarf, the remnants of stars that died violent deaths. The pulsar is a neutron star, the collapsed core of a massive star that exploded as a supernova. That explosion should have obliterated any nearby planets, scattering them into the void. Yet this world endured, continuing its orbit through the aftermath of stellar death. What makes its existence even more baffling is the metallicity problem. Planets form from disks of gas and dust around young stars. That dust contains heavy elements, carbon, silicon, iron, produced by previous generations of stars. But 12.7 billion years ago, the universe contained almost no heavy elements. The first stars had only recently formed. There simply wasn't enough material to build planets through conventional core accretion. The planet's mass is approximately 2.5 times that of Jupiter. It orbits both stars in a wide circumbinary orbit, completing one revolution every century. Its formation challenges our models. Its survival defies expectations, and its longevity dwarfs anything in our solar system. This ancient wanderer has existed for nearly 3 times longer than Earth, orbiting in the darkness of a globular cluster where thousands of stars crowd together in a space just dozens of light years across. How many other impossible worlds might be hiding in ancient star clusters, silently orbiting the corpses of their creators, bearing witness to nearly the entire history of the universe? Number 8, XLSSC 122, the Impossible Galaxy Cluster. In 2015, astronomers analyzing data from the European Space Agency's XMM Newton X-ray Observatory detected something that shouldn't exist. At a distance of 10.4 billion light-years, they found a fully formed galaxy cluster containing hundreds of trillions of solar masses, glowing with X-ray emission from gas heated to tens of millions of degrees. The cluster existed when the universe was just 3.4 billion years old, barely a quarter of its current age. This timing creates an impossible problem. Galaxy clusters are the largest gravitationally bound structures in the universe, requiring immense spans of time to assemble. Matter must first clump into dark matter halos, then galaxies must form within those halos, then those galaxies must gravitationally attract each other over hundreds of millions of light years, and finally the entire system must settle into dynamical equilibrium. According to standard cosmological models based on lambda cold dark matter theory, XLSSC 122 required more time to form than the universe had existed. Computer simulations predict that clusters this massive shouldn't appear until at least 5 to 6 billion years after the Big Bang. Yet here it was, 2 billion years too early, its X-ray signature indicating a mature, virialized system rather than a young cluster still assembling. The cluster's mass approaches 100 trillion solar masses. Its member galaxies show red sequence colors, meaning their stars are old, their star formation mostly complete. Everything about XLSSC 122 speaks of age and stability. It shouldn't merely exist, it shouldn't be finished. Scientists theorize the cluster formed in an unusually dense region of the early universe, where primordial density fluctuations were larger than average. Such regions are statistically rare, occurring perhaps once in 1,000 comparable volumes of space. The explanation makes XLSSC 122 improbable but not impossible. What remains unsettling is that this cluster represents the extreme tail of statistical distribution. It exists at the very edge of what our models allow. If it were only slightly more massive, or existed slightly earlier, no amount of statistical reasoning could explain it away. How many other cosmic structures are we discovering at the limits of physical possibility? Number 7. Ancient oxygen in Max 1149 JD1. On May 16, 2018, researchers led by Takuya Hashimoto published a discovery in Nature that compressed the timeline of stellar evolution beyond recognition. Using the Atacama Large Millimeter Array, they had detected oxygen in a galaxy 13.28 billion light-years away. The light had been traveling toward Earth for so long that it showed us this galaxy as it existed just 500 million years after the Big Bang. This was the oldest oxygen ever found in the universe. Oxygen doesn't exist naturally in the cosmos. It cannot form during the Big Bang, which produced only hydrogen, helium, and traces of lithium. Oxygen forms exclusively in the nuclear furnaces of massive stars, and only escapes into space when those stars die as supernovas. The detection of oxygen in Max 1149 JD1 meant that stars had already completed their entire life cycle at an epoch when the universe was barely 3.6% of its current age. The implications are staggering. Massive stars that produce oxygen live only a few million years before exploding. But for detectable oxygen to accumulate in a galaxy's interstellar medium requires multiple generations of star formation and death. The stellar population analysis suggested stars in this galaxy had been forming for 250 to 300 million years before the observation. That means the first stars in the system ignited just 200 million years after the Big Bang, in an era cosmologists call the cosmic dawn. Standard stellar evolution models don't predict such rapid chemical enrichment. The first generation of stars, population 3 stars, composed purely of primordial hydrogen and helium, should have been extraordinarily massive, living fast and dying young in spectacular supernovae that seeded space with the first heavy elements. But the timeline, Max 1149, JD1 demands, is even more compressed than the most aggressive models predict. The galaxy itself appears unremarkable otherwise, containing roughly 1 billion solar masses of stars in a compact region just a few thousand light-years across. What distinguishes it is not what it is, but when it is. The oxygen signature proves that the engines of stellar death were already running at full capacity, while the universe was still in its infancy, transforming pristine hydrogen into the building blocks of planets and life with almost unimaginable speed. Number 6. Pristine population 3 gas clouds. In 2011, Michel Fumagalli and his colleagues at Carnegie Observatories were analyzing light from distant quasars using the Keck Observatory's high-resolution spectrograph when they noticed something extraordinary. The light had passed through clouds of gas billions of light-years from Earth, and those clouds had left absorption signatures in the quasar's spectrum. But some signatures were notable for what they didn't show. No carbon, no oxygen, no silicon or iron, just hydrogen and helium, the only elements created in the Big Bang. These gas clouds contain no heavy elements whatsoever. Their metallicity is so low it falls below detection limits, less than 100,000th of the sun's metal content, possibly zero. They represent pockets of space that have somehow remained pristine for over 13 billion years, untouched by the pollution of stellar death that has contaminated virtually everything else in the universe. Every star that has ever exploded as a supernova scattered heavy elements into space. Every generation of stars recycled that material, incorporating metals into new stellar systems. The interstellar medium became progressively enriched with carbon from dying red giants, oxygen from massive stars, iron from supernova cores. By the time our solar system formed 4.6 billion years ago, the gas cloud that birthed the sun contained enough metals to build rocky planets. But these clouds remember the beginning. They exist in remote regions of the intergalactic medium, far from galaxies, isolated in the vast cosmic web of dark matter and gas that spans the space between galaxy clusters. Somehow they avoided enrichment. No nearby supernovae contaminated them. No galactic winds reached them. They drifted through billions of years of cosmic history, passive witnesses to the chemical evolution of everything around them, yet remaining fundamentally unchanged. Scientists theorize these clouds survived in low-density voids or shadow regions shielded from metal-enriched outflows by the geometry of cosmic structure, but the exact mechanisms that preserved their pristine nature for so long remain unclear. What's particularly unsettling is their rarity. Among thousands of absorption systems surveyed, only a handful show this level of chemical purity. Most gas at these epochs already shows metal contamination. These clouds are relics, fossils of creation floating in an ocean of recycled matter. What else from the universe's first moments might still exist in isolated corners of space, waiting to be discovered? Number 5. The Himiko Cloud. In 2009, Masami Ouchi and his team at Carnegie Observatories were conducting a survey of the early universe using the Subaru telescope in Hawaii when they discovered something unprecedented. At a distance of 12.9 billion light-years, existing just 800 million years after the Big Bang, they had found an enormous cloud of hydrogen gas glowing with intense Lyman alpha radiation. They named it Himiko, after a legendary queen of ancient Japan, and its properties defied every expectation. The cloud spans 55,000 light-years, comparable to the diameter of the Milky Way. Its Lyman alpha luminosity exceeds 10 trillion times that of the Sun, requiring massive energy input from an unknown source. When examined with higher resolution instruments, Himiko revealed 3 distinct clumps of emission, suggesting multiple components in gravitational interaction. Yet, unlike typical galaxies, no obvious massive galaxy or bright point source sits at its center. The power source remains mysterious. Star formation distributed across the structure could generate the observed luminosity, but would require roughly 100 to 200 solar masses worth of new stars forming every year. An obscured supermassive black hole could also produce the energy, but X-ray observations have detected no such object. Some scientists propose gravitational heating as gas collapses into the dark matter halo, releasing energy as matter falls inward. Others suggest Himiko represents a major merger of protogalaxies, capturing the exact moment when smaller systems collide and coalesce into something larger. What makes Himiko particularly striking is that we may be witnessing a process that normally remains hidden. Galaxy formation theories predict that massive galaxies assemble through mergers and accretion, but we rarely catch them in the act. Himiko's enormous size, early epoch, and peculiar structure suggest we're observing the birth process itself, seeing a massive galaxy coming together in real time as viewed from across 12.9 billion years of cosmic history. The 3 clumps may be independent protogalaxies spiraling together, their gas reservoirs colliding and igniting with radiation as they merge into a single massive system that will eventually become indistinguishable from other ancient elliptical galaxies scattered throughout the present-day universe. Number 4. Ancient water in V883 Orionis. On March 8, 2023, researchers led by John Tobin at the National Radio Astronomy Observatory published a discovery that connected our existence to the deep past in the most intimate way possible. Using the Atacama Large Millimeter Array in Chile, they had analyzed water molecules in a protoplanetary disk surrounding a young star 1,305 light-years away in the constellation Orion. What they found was a chemical fingerprint that matched Earth's oceans with startling precision. Water molecules come in different isotopic forms. Most contain 2 ordinary hydrogen atoms, but some contain deuterium, a heavy isotope of hydrogen with an extra neutron. The ratio of deuterium to hydrogen serves as a signature, a fingerprint that reveals where and when water formed. The water in V883 Orionis' disk has the same deuterium to hydrogen ratio as the water on Earth, 1 to 6,000 in our oceans. In every raindrop, in every living cell, this match proves something profound. The water on Earth didn't form here. It predates our solar system entirely. It formed in the cold molecular cloud that collapsed to create the Sun 4.6 billion years ago, or even earlier in the interstellar medium before that cloud assembled. The molecules in Earth's oceans are older than the star that gives us life. Water forms when hydrogen and oxygen meet in the frigid darkness of space, freezing onto dust grains at temperatures just tens of degrees above absolute zero. The deuterium enrichment occurs through ion molecule chemistry in these cold clouds, creating a specific ratio that remains locked into the ice. When molecular clouds collapse to form stars and planets, this ancient water is inherited largely unchanged, carried forward from the interstellar medium into interplanetary systems. Every ocean that has ever crashed against a shore, every glacier that has carved a valley, every storm that has drenched a forest, all of it is built from molecules that remember a time before the sun existed. When you drink water, you're consuming material older than our world, a substance that has witnessed the birth and death of stars, that travel through the galaxy for unknown eons before becoming part of Earth. What other pieces of our world carry memories of a time before our beginning? Number 3, Glasses 13, the galaxy that shouldn't exist. In July 2022, just weeks after the James Webb Space Telescope began operations, astronomer Rohan Naidu and his team at the Harvard-Smithsonian Center for Astrophysics announced a discovery that challenged our understanding of cosmic history. Using JWST's unprecedented infrared sensitivity, they had identified a galaxy at a photometric redshift of approximately 13, meaning its light had been traveling toward us for over 13.5 billion years. The galaxy existed just 300 million years after the Big Bang, in an era when the universe was barely 2% of its current age. Glasses 13 isn't a small clump of stars forming for the first time. It appears to be a fully structured galaxy, with organized stellar populations and active star formation, containing roughly a billion solar masses of stars in a compact region only 1,600 light-years across. Its existence creates a temporal paradox. Galaxy formation, according to standard lambda cold dark matter cosmology, requires extended periods of time. First, dark matter must gravitationally collapse into halos, then gas must cool and condense within those halos. Stars must form, creating feedback that regulates subsequent star formation. Structure must emerge from initial chaos. This process takes billions of years in conventional models. Glasses 13 had less than 1 billion. Computer simulations of structure formation in the early universe predict that galaxies this massive shouldn't appear until several hundred million years later. Yet James Webb keeps finding them, galaxy after galaxy that formed faster than physics should allow. The discovery forces uncomfortable questions. Either our models of galaxy formation are fundamentally incomplete, missing some mechanism that allows rapid assembly in the early universe, or the conditions in the first billion years after the Big Bang were radically different from what we've assumed. Perhaps dark matter behaved differently. Perhaps star formation proceeded with far greater efficiency. Perhaps the primordial density fluctuations were larger than our measurements of the cosmic microwave background suggest. Glasses 13 and its contemporaries represent more than distant objects. They represent a crisis in cosmology, a systematic tension between observation and theory that refuses to resolve. Every new galaxy JWST discovers at these extreme distances adds to the problem, demonstrating that rapid structure formation in the early universe wasn't a fluke, but a pattern we don't yet understand. Number 2, J03131806, the black hole from the dawn of time. On January 12, 2021, astronomer Feige Wang and his team at the University of Arizona announced a discovery that violated the fundamental laws governing how quickly black holes can grow. Using the Gemini North Telescope and Keck Observatory, they had identified a quasar at redshift 7.64, its light reaching us from 13.03 billion years in the past. At the heart of this ancient beacon sat a supermassive black hole containing 1.6 billion times the mass of our Sun. It existed just 670 million years after the Big Bang. The problem is mathematical and absolute. Black holes grow by consuming matter, but there's a speed limit to this process called the Eddington limit. As matter spirals into a black hole, friction heats it to millions of degrees, producing radiation that pushes against infalling material. This radiation pressure creates a natural brake on growth, even feeding continuously at the maximum Eddington rate. A black hole would need roughly 800 to 900 million years to grow from stellar mass seeds of 10 to 100 solar masses up to 1.6 billion solar masses. J03131806 didn't have that much time. The first stars needed approximately 100 to 200 million years to form after the Big Bang. Those stars had to live out their lives and collapse into black holes, providing the seeds that would grow into supermassive monsters. That leaves only 470 to 570 million years for actual growth. The timeline doesn't work. The mathematics forbid it. Scientists have proposed exotic solutions. Perhaps direct collapse black holes formed in the early universe, creating seeds of 10,000 to 100,000 solar masses without requiring stellar intermediaries. Perhaps black holes in the early cosmos accreted faster than the Eddington limit, feeding in super Eddington bursts that violated theoretical expectations. Perhaps primordial black holes formed in the first seconds after the Big Bang, providing ready-made seeds. But J03131806 isn't alone. Astronomers have discovered multiple supermassive black holes at similar epochs, each one presenting the same impossible growth rate. This isn't isn't a measurement error or a unique object. It's a systematic problem affecting our understanding of how the universe's most massive objects came to be. The black holes exist. The timeline doesn't allow them. Something in our models is fundamentally wrong. Number 1. The cosmic microwave background. Cold spot. The oldest thing we can observe in the universe isn't an object. It's light itself. The cosmic microwave background radiation that fills all of space. The afterglow of creation. This light was released 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and photons to travel freely. That light has been journeying through space for 13.8 billion years, making it the most ancient observable phenomenon in existence. And within this relic of the beginning, there is a scar. In August 2004, Lawrence Rudnick and his team at the University of Minnesota identified an anomaly in data from the Wilkinson Microwave Anisotropy Probe. A region of the sky in the constellation Eridanus, spanning approximately 5 degrees across, was colder than its surroundings. Not by much, only 70 millionths of a degree Celsius. But in the remarkably uniform cosmic microwave background, this difference was staggering. The European Space Agency's Planck satellite confirmed the finding in 2013 with even higher precision. The cold spot spans roughly 1.8 billion light-years and represents a temperature deficit that shouldn't exist, according to standard inflationary cosmology. Computer simulations suggest a feature this extreme should appear by random chance only 1 to 2% of the time. In 2015, astronomers discovered a supervoid in the same direction, a region of space containing fewer galaxies than expected. The void could explain part of the temperature deficit through the integrated Sachs-Wolf effect, where photons lose energy traversing underdense regions. But the void accounts for only about 20 to 30% of the observed cooling. The majority remains unexplained. Some cosmologists suggest it's a primordial fluctuation, an unlikely but natural deviation amplified by cosmic inflation. Others propose more exotic explanations. Could it be a topological defect? A scar in space-time from the universe's first moments? Could it represent evidence of physics beyond the standard model? One particularly controversial theory, proposed by Laura Mersini-Houghton at the University of North Carolina, suggests the cold spot could be a bruise from collision with a parallel universe during the inflationary epoch, a place where the membrane of our cosmic bubble pressed against another reality. The cold spot exists at the observable edge of space and time. It is literally embedded in the oldest light we can detect, a mystery written into the fabric of the universe before galaxies existed, before stars ignited, before structure of any kind emerged from the primordial plasma. We are observing an anomaly that predates everything we can see, a wound on creation itself whose cause may originate from beyond our universe, from a time or place where our physics no longer apply. This isn't just the oldest thing we've found in space. It's a scar on the face of reality, and we may never know what created it.